Hello, everyone. Again, today, this is another seminar series from USACM student chapter. So before the introduction of our speaker, I would like to encourage all you who are watching this in a offline manner, or you are right now joining us. Please do register in our Discord and check our content over there. And also we have a YouTube channel which we put the videos of these seminars over there as a way to distribute the seminar content. So we are interested to present everybody work. So please send your great work to us. Please reach out to us with this email and introduce what you are interested to present with abstract and also a short biography of yourself. And we will try to contact you back and arrange because we have every month we are trying to have one seminar. We are trying to organize that accordingly. And today I have it's my great pleasure to introduce today's speaker, Dr. Masih Al-Sedi, who is right now postdoctoral research at UC San Diego. And he's going to introduce his amazing work on closed form error bounds for finite-dimensional Koopman-Based models and implication for learning.
Thank you so much. So my name is Masih Al-Sedi. I'm a postdoc at UCSD working with Professor Jorge Cortez. And today I want to talk about some of our most recent works on finding closed form error bonds for finite-dimensional Koopman-based models that come from orthogonal projections. So to motivate you a little bit, in recent years, we have witnessed a surge in data-driven methods that try to learn dynamical behavior or at least extract some information about the system's behavior. And there are a lot of different applications, but most of these methods fall under the umbrella term of machine learning. So machine learning is a very broad term. You have some very rigorous methods that come with guarantees, and you also have complicated methods that lead to amazing results, but we don't understand them. So you can say that the machine understands how the system works, but we do not understand the model that the machine gives us. Our goal here is to be theoretically principled and also have models that are explainable. And to do so, we are going to use a tool called Koopman operator. So in this presentation, I will first give you a background on Koopman operator, and then I will talk about data-driven error bonds on finite-dimensional Koopman-based models. And I will briefly talk about implications of these bonds for robust learning. And at the end, I just talk about only briefly about how you generalize these error bonds on inner product spaces. So let's get started with the Koopman operator. But before seeing the definition, I want you to pay attention to the simple nonlinear equation. And if you are a controls person like me, the way you try to understand this is that you first start to find the fixed points or any other attractor, then try to decide its stability and regions of attractions and so on. But for this specific system, we can do something better. We can find the global change of coordinates, which is a bijective map, and we can put the system into a form that looks linear. Then you can find a closed form solution for the system, and then it gives you a closed form solution for your original nonlinear system. You also can do something else. You can just embed this into a larger linear system, find a closed form solution for it, which gives you a closed form solution for your nonlinear system. So it would have been amazing if we could do this for every system, but we cannot. However, this idea can be generalized if we are willing to make some compromises, which brings us to the Koopman operator. So consider a dynamical system that is nonlinear and discrete time and defined by this map T. And also consider a vector space of functions on the field of complex numbers. And each function is a map from the state space to complex number. And also we enforce this vector space to be closed under composition with our dynamic map, which means that for every function in our functional space, the composition with T is also in the function space. So if we have all these in place, we can define the Koopman operator on our functional space in a way that it maps every function to its composition with the dynamic map. And you can look at this through the lens of pushing forward the value of the function across all trajectories starting from every initial condition by one time step, and then putting all that information into a new function. This is a very simple definition and a useful one. It has some nice properties. The first thing is it is a linear operator, and it directly comes from the definition. But more importantly, the eigenfunctions of this operator evolve linearly on the trajectories of the system. For example, here I have a non-zero function phi, which is an eigenfunction with eigenvalue lambda. And if you check the definition of the Koopman operator, you see that on a system trajectory, the value of the function gets scaled by lambda as you move forward in time, that you see in the picture on the right-hand side. And combining these two types of linearity in time and space can give you a very good way of efficient computation that turns everything, if you can do finite dimensional models, turns everything into numerical linear algebra. So let's go back to this toy example that I showed you earlier, and we are going to see how you can define a Koopman operator for it and how eigenfunctions behave. To define a Koopman operator, I define my function space as one of these functions, and I'm abusing the notation a bit. Every element here is a function. For example, that one is a constant function of the state that takes the state and returns one for every state. And everything else is also a function. And it is easy to check that this space is closed under composition with my dynamic map, which means that I have a well-defined Koopman operator. And these are all the eigenfunctions in my space. So let's take a look at how these eigenfunctions behave with respect to the system trajectories. Consider on the right-hand side, you see an initial condition, but denoted by a blue diamond in the state space. And also consider the second eigenfunction in red. Right now, I know the eigenfunction, I know the initial condition, and I know my eigenvalue. So I can use that identity on top right and find the value of the eigenfunction on my trajectory as I move forward in time. And for every value, that defines a level set for my function. So basically, what I can say is that my trajectory will cross these level sets from right to left as I move forward in time. However, this does not give me complete information about the system behavior. But let's do this for another eigenfunction. For example, the fourth eigenfunction. Again, I can find these level sets, and I know that my trajectory jumps from right to left as I move forward in time and crosses these level sets. Again, I don't have complete information. But if I combine these two eigenfunctions at the same time, you see that for every pair of curves with the same color, they intersect exactly at one point, which means that my trajectory must be at those points. And these two eigenfunctions completely give me a representation of the system. And if you remember at the beginning of the talk, I gave you a general change of coordinates. And these two eigenfunctions were those change of coordinates. So now that we have seen this, you might think that, okay, life is great, and we go and turn everything into a nonlinear system. But there is a problem. We turn everything into a linear system, but there is a problem. And the problem is that we don't always have these finite dimensional representations, and the functional space is generally infinite dimensional. And the reason is that we need to be closed under composition with our dynamic map. So for computation, however, we need finite dimensional models, at least for many applications. So how can we find these? Let's define a problem in a way that you have a Koopman operator on some functional space, and someone gives you a finite dimensional subspace here denoted by S. And we are going to find or approximate the action of K on S. So one case is that if S is invariant under the application of the operator, which means that if I take any function in S and apply the Koopman operator, I stay in S, then I can simply restrict the domain of K to S, and I have a well-defined operator from S to S. And I can take a basis for S, show this operator by a matrix, put it into a computer, and we are done. However, if S is not invariant, we have a problem. Let's say I have a function f, and I apply the operator and go out of the space. So I cannot have an operator from S to S, not directly by restricting the domain of the Koopman operator. But what I can do is to approximate this function kf by something on S. And if you have an inner product on your space, the best approximation comes from our orthogonal projection. Here, the piece of S is the orthogonal projection operator on a space S. And in this case, I'm going to approximate K with P sub S times K. And note that under this new operator, the space S is invariant, so I can do the trick that I did above. So this is a very brief introduction of how you find finite dimensional forms. But our goal was to do everything with data. Which brings us to a special case of this projection called the extended dynamic mode decomposition method. Here, again, we have a finite dimensional space that we define by a dictionary of functions or a basis if they are linearly independent. And I should say that my notation here is transpose of the general notation in the literature because it makes computation easier. So I show this by a row vector. And also here, I don't have the dynamics, but I can go and gather data. And the way I gather data is that I go to system trajectories. I put two consecutive points. I take two consecutive points and put them into two data matrices, X and Y. And then I can apply my dictionary on every row of these data matrices. And EDMD method is simply, you can do it by least squares as follows. And this KEDMD is basically representation of an operator that comes from a projection. And this representation is based on the basis D. So if you change your basis, you have the same operator, but with a different representation. Well, EDMD is a very simple method. That's why it is very popular. And in fact, you can find the solution in closed form. And also we should note that at the end of the day, Koopman operator works on functions. So you want to approximate functions. And here we have approximation of KF, which is basically a projection, by this formula P sub KF, which you first put your vector V that represents F with respect to the basis through the EDMD matrix, then multiply by the dictionary. And also, we can have a linear dynamical predictor in the sense that you just push forward the values of the dictionary one time step by multiplying by this KEDMD. And on the bottom right, you have the closed form solution over a K step trajectory. So this is because it's simple, it has a lot of applications, and people like it. This is a very old slide. I think the most recent publication is from 2021. And it is just to make a point that you can use it for a lot of things. But also we need to be mindful that we had a linear predictor, which was an approximation. So we have to be careful whether this approximation is accurate or not. And it is not that simple. So let me show you again a toy example. But this time, let's say I am going to take two dictionaries, D1 and D2. And obviously D1 is larger and contains D2. And I'm going to take some data, do EDMD, and here I'm plotting the relative error of the EDMD predictor over one trajectory of the system. And we see that the first dictionary does not give us good prediction for all functions. So you can see that the error goes above 100% after just 2 time steps. While the second dictionary, the smaller one, gives us exact prediction. So this example shows us that we need to choose the dictionary carefully. And also just adding functions does not help. I should note that there are asymptotic results about when the dimension goes to infinity, you can capture the spectrum of the Koopman operator under some conditions or capture the eigenfunctions. I believe the convergence is weak, but I'm not sure. I have to check. But again, those results are asymptotic. And the dimension needs to go to infinity. So if the dimension goes from 10 to 20, there is no monotonicity. So things are not supposed to necessarily get better. So to find a good dictionary, first we need to understand what is special about the second dictionary that gives us an exact prediction. And the special property is that it spans an invariant subspace under the Koopman operator, which means that because it is invariant, the projection error is 0. You are in the space, you project on the space, and there is no error. You get the same function. So now let's go and find some error bounds or models that can help us to learn the right space or dictionary. But before we get there, this is a typical way that people use to find the right dictionary. They basically form this optimization problem. The cost function is the EDMD, the residual error of the EDMD problem. However, in EDMD, we minimize over K. Here we are minimizing over D that belongs to some parametric family of functions, which is generally neural networks or polynomials or something else. And on the right-hand side, I just plugged in the closed form solution of EDMD, so you know that this is a highly non-convex problem. And the reason that people use this scheme is as follows. If you have a dictionary that spans a Koopman invariant subspace, that error is 0. And you can have arguments in the opposite direction, even though you need some additional conditions, but we have some results that are with probability 1 as the number of samples go to infinity, you can say the span of D is Koopman invariant. But there is a problem. And the problem is that in a real world, you do not get exact invariance and you do not get exactly 0 residual error. You are approximating. So does this argument hold for approximations? Let's see. If you have a close to invariant space, then you can say that this error is close to 0. You can make that argument. However, this is not what we need. What we need is to minimize this error over some parametric family, and hopefully we get something close to 0. Then we want to claim that the span of D is approximately invariant under the Koopman operator. But can we make this claim? Let me show you an example. Consider a linear system, one-dimensional, very simple. And also consider a two-dimensional function space. Here I have a span of x and x cubed minus x squared. And for this function space, I build a family of bases parameterized by a parameter alpha. So note that a span of the alpha is the same for all values of alpha that are non-zero. And I'm going to plot the residual error of EDMD. Here you can see that even though my space is not invariant, I can change my basis in a way that I can make this error as close to 0 as I want. So a small error does not mean close to invariant subspace. And the first thing that comes to mind when you see this plot is, can I do better if I normalize this error? Well, apparently, no, you cannot. Again, I can make this error, this time normalized, this is a relative error. I can make it as close to 0 as I want by changing my alpha. But the thing is that even though the error is close to 0, the space is the same and it is not close to invariant. So when we can come back to this slide and see that no, you really cannot make a claim in the opposite direction. And we need to fix this. So the way we fix it is has a very simple idea, even though the math is not that simple, but I'm not gonna get into that. And the idea is that if you have a linear system that is non-singular, when you run it backward in time, you get another linear system with an inverse matrix. And to see how it is useful, first, I am going to define some notation. And here, Kf and Kb are the solutions of EDMD done forward in time and backward in time. And backward means that I just flip the order of my data. And also, I have an assumption, which is very typical, that these data matrices that I have full column rank. So when a span of the dictionary was invariant, EDMD gave us an exact linear system, which means that Kf times Kb is identity. And the way I'm going to measure closeness to invariance is by measuring how much the product of Kf and Kb deviates from being close to identity. So I have this idea of consistency matrix, identity minus Kf times Kb, and I take the spectral radius of this matrix as something we call consistency index. And I will tell you why a spectral radius is important. So, and for those of you who don't know the definition, it is just the maximum of the absolute value of the eigenvalue. So let's see the properties of consistency matrix and consistency index. For your reference, we have the definitions and notation on the right-hand side. And let's go and see. First, property is that the spectrum of this matrix only depends on the span of the dictionary and data, not the dictionary itself. Which means that the eigenvalues do not change if I change the basis for my subspace, which was a problem with the residual error that I showed you earlier. And also, this matrix is similar to a positive semi-definite matrix, which helps a lot with numerical computations. And all the eigenvalues are real and belong to 0 and 1. And this is very helpful because then a spectral radius is just the maximum eigenvalue. And the main result in this slide is that the square root of consistency index is the maximum relative error of the action of the operator approximated by EDMD over all functions in the span of the dictionary. Now you can probably see why this does not depend on a basis, because instead of working with finitely many functions in a basis, we are considering all uncountably many functions in our vector space and taking the maximum relative error over all of them. So if I go back to this, example, you can see that this time the consistency index does not change based on the changing of the alpha, and this solves our problem. Now let's see how you can use it for robust learning. You can, instead of the residual error of EDMD, basically take the consistency index, which is equivalent to this min-max problem. But for the max part, you have a closed form solution. And this has some nice properties. One is that it is not sensitive to a scaling of your optimization variables. And it is not sensitive to the choice of basis for your space. It is resilient against overfitting. You almost never overfit. And you don't need any regularization or any other hacks to make this work. So let's see if it works on a simple example. I have a damped pendulum, and I want to just find the 5-dimensional space. And my dictionary has the states in it because I want the states to predict them. And I have 3 other functions with a feed-forward neural network. And again, the linear predictor of EDMD is at the bottom. And I'm going to just take some data, train this neural network and build a linear predictor. On the right-hand side, you can see the linear prediction. There are three cases. You have the exact data over time, which is orange. And then you have the solution of the linear predictor trained by our method consistency index in blue. And you can tell that it is almost exact, even though the predictor is linear. And the green one shows the traditional method, the linear predictor based on the residual error of EDMD, which does well for around 80 time steps, but it falls apart after a while. And we have the same situation for the angular velocity. Again, the residual error does not do well over time. So I'm going to very briefly show you how you can generalize it and give you some references, even though I'm not going to get into the math for this part. Now, consider that you don't have data. You just have this function space S, F, and some finite dimensional subspace S. And I'm going to equip F with some inner product that induces a norm and a metric. And if the subspace is not invariant, you have this picture that I showed you earlier that you go out of this space and you orthogonally project back. And the approximation was that you had an operator K, you approximated with PS times K, and then built your approximation. Here, I just have the same approximation, but just define some notation called a K approx. And we have a more general error we call invariance proximity of subspace S under operator K, which is basically supremum of the relative error of the prediction over all functions in S. And you have already seen a data-driven case of this, but the question is, can you compute this in closed form over a general case? And the answer is yes. This is the sign of the maximum Jordan principal angle between the subspace S and its image under operator K. And you can, if you are interested, the second paper below shows you a way of how you can turn this into numerical linear algebra and just compute. With this, I'm going to end the presentation. And thank you for your attention. These are the references that you can check out. And I'm happy to have your questions. Thank you.
Thank you, Mercy. It was really interesting. Very good job.
Thank you so much.
So please put your question in the chat or just directly ask. Unmute yourself and ask. Is there any question or?
I have a quick question. So in your dictionary, I saw that you used polynomial functions in most of the earlier examples. So is this analysis extended to other kinds of functions also, like if you have sines or exponentials or other functions in your dictionary?
Oh, yes, yes. So there is no condition for our case. You generally need to have some, let me go back. And so you have this function space F here, and that needs to be closed under composition with the map that you have. And this space is generally, you consider the L2 space over some measure. So it does not need to be polynomial. However, if you have a polynomial system and you want to hook up some example for presentation, obviously you use polynomials, but no, not in general.
Thank you.
Of course.
Yeah, I think in fact you also showed some cases with neural network, right?
Yes, at the end.
Yeah. Any other question from the? If not, I have some questions. So I think I didn't get this part. That like I'm not sure that was like. So you mentioned the optimization at the end you propose is to control the maximum eigenvalues of some system, right?
Yes.
like how do you, like when you use the dictionary as a neural network, how do you, because I guess it's gonna be like sophisticated optimization problem. How do you solve that?
So it's solving, basically, I'm going to do a stochastic gradient descent.
Oh, okay. It's
And
just okay.
yeah.
Okay.
Yeah,
Because
so it's a neural
usually,
network, so I'm not gonna do.
okay, okay. Because at the beginning everything was in a linear and classical setup, which people from control they do the exact analytical optimization. But in here, I was curious if it's still possible or no. Of course, it's not possible.
Yes, but we have some algebraic methods that if you write them as optimization, they are not going to pan out. You cannot find them, but we can find exact solutions. But those are searches within a vector space. For example, you choose some vector space, like all polynomials up to degree like 20. That's not a good space. But what you go, actually, I can go back. I had an example which is from one of those papers, which is this one. And you search through some space, and we have algorithms that find the maximal invariant subspace. And this is an example that the space, the search space was a span of B1. If you write this as an optimization and try to find it, you cannot. But because it has a nice algebraic structure, you can do some iterative algorithm that finds the right space for you.
That's true, but I guess even like in that sense, in the optimization sense, if you start with a good initialization, still you can.
Yes, but you need to know something.
Okay, yeah, the structure. Yeah, you can put that. That's correct. The structure. You need to have sort of understanding of the structure at the beginning.
Yes.
And another question I had, I forgot. Let's see if other people has questions, then I can. Oh, I did this question. In the functions in your dictionary, how important is to be orthogonal, or it doesn't matter at all?
So for this case of consistency index, it doesn't matter. And the reason is that it doesn't at all, because the consistency index does not depend on your basis. So you can see it. If I change the basis, I have some measure of how good the subspace is. So that's one of the things that when you do this optimization, you do not need to try hard to make things work well.
I see. And also, you don't enforce like the sparsity in your case.
Oh, no, we don't. Because again, sparsity is a property of your basis. So if you change the basis, you can break the sparsity. And we didn't want to be sensitive to that, because in many cases, the sparsity is useful if you know you have some sparsity pattern. But if you don't know, then, or you know there is one in some coordinates that you don't know, that again has some problems.
Because the issue in terms of optimization, when you work with like a dictionary of functions that are not orthogonal, the sparsity is not just about just the sparsity, but also it makes sure you're not doing redundant stuff, which makes your optimization kernel like ill behave.
Yes. And so again, you don't have this problem here. If you have that kind of ill behavior, the consistency index will be 1. And 1 is the maximum value. So as long as you're minimizing,
I see.
You know that never happens.
Oh, that's interesting. So that's why you said you don't need regularizer, I guess.
Yes, that's true. Yes.
Okay. Very, very interesting. So any other question from audience? If not, we can thank Messi, and that's it.
Thank you so
Messi.
much.
Thanks for your time. It was really interesting talk. I like it.
Yes. Thank you for the invitation. I really appreciate it.
Have a good day.